Have you ever stopped to wonder how your phone knows it's you just by looking at your face? Or how an app can translate what you're saying, like in real time? Well, the secret behind all that magic is a technology that's actually inspired by our very own brains. It's called an artificial neural network, or ANN. So let's dive in and really unpack how these digital brains work.
So let's start with a question that really gets to the core of it all. How on earth can a computer learn to do something so human, so complex? Our brains, they can recognize a familiar face in less than 300 milliseconds. For the longest time, that was an impossible task for a computer. So how did we finally get them to catch up?
Well, the answer is right there in the definition. See, an ANN isn't just another computer program. It's a totally different kind of processor, one that's designed from the ground up to learn from experience. Just like us, it learns about the world around it, and it stores that knowledge not in some neat little memory file, but in the web of connections between all of its parts.
And that's because the entire concept is based on the ultimate blueprint, the human brain. I mean, think about it. It's this unbelievably complex, nonlinear, parallel processing supercomputer. Researchers looked at how incredibly efficient our brains are and basically said, okay, what if we could build a computer that works in the exact same way?
So to understand this massive, complex network, we've got to zoom way in. We need to start with the single, most fundamental building block. Let's get to know the digital brain cell, the artificial neuron.
And check this out. This slide just lays it out so perfectly. It's a beautiful piece of biomimicry. In our brains, we have dendrites that receive signals. And in ANN, those are just called inputs. You can see them there labeled with an X. Our cell body processes all those signals. The artificial neuron has a summing junction to do the same thing. But here's the really crucial part. The strength of a connection in our brain, the synapse, is represented by a synaptic weight, or W. It's literally a digital copy of a biological idea.
So, how does one of these artificial neurons actually fire? Well, it's a pretty simple three-step dance. First, it gets a bunch of inputs, and each one is multiplied by its own weight to decide how important it is. Second, it just adds all those weighted inputs up. And finally, that total sum gets passed to something called an activation function. Just think of it like a bouncer at a club. If the total signal is strong enough, the gate opens, the neuron fires, and the message gets passed along. If it's too weak, it just stays quiet.
Okay, but a single neuron on its own it's not that smart. It's basically just a simple calculator. The real power, the actual intelligence, that only emerges when we connect millions or even billions of them together into a network. So let's see how that's done.
Turns out there are two main ways you can wire these things up. The most common one is the feedforward network. Here, information flows just like a one-way street, straight from the input through the middle to the output. No U-turns allowed. But then you have recurrent networks. These guys have feedback loops, which means information can actually flow backward and get reprocessed. It's much more like a busy two-way street with a bunch of roundabouts.
So let's take a closer look inside that one-way street, the feedforward network. It always starts with an input layer, which just takes in the raw data, like say all the pixels from an image. Then, that data gets passed through one or more hidden layers. Now these are the famous black boxes, where all the really complex, abstract thinking happens. And finally, you get to the output layer, which spits out the final answer. In most of these networks, every single neuron in one layer is connected to every single neuron in the next. That's why we call them fully connected.
Right, so we've built the structure. But here's the thing. These networks aren't programmed with a bunch of rules. They actually have to learn the rules themselves. And just like people, they have a few different ways of learning. Let's explore the three main strategies that make these networks so incredibly smart.
First on the list is supervised learning. The best way to think about this is learning with the teacher. You show the network, say, 10,000 pictures of cats, and every single one is labeled cat. The network takes a guess. If it's wrong, the teacher sends back what's called an error signal, basically telling it how wrong it was. And then the network adjusts all its internal connections, its weights, to try and get a little bit closer to the right answer next time.
Next up, we have unsupervised learning. Now this is more like being a detective. The network gets a massive mountain of data, but this time there are no labels, no clues, no answers in the back of the book. Its job is to find the hidden patterns and structures all by itself. For example, it might look at customer data and figure out how to cluster people into different buying groups without ever being told what those groups should be.
And finally, there's reinforcement learning. This one is exactly like training a pet. The network performs an action out in the world, like moving a piece in a game of Go.
If that action leads to a better board position, it gets a reward, a little digital treat. If it makes a bad move, it gets a penalty. You let it do this millions and millions of times, and eventually it learns the sequence of actions that gets it the biggest possible reward at the end.
So yeah, these networks are obviously incredibly powerful. But like with any game-changing technology, they have some really amazing strengths and some very real weaknesses. So let's take a look at the final scorecard, the pros and the cons.
Let's start with the superpowers, because they are seriously cool. They're amazing at handling nonlinearity, which just means they can solve messy, real-world problems where the rules are not simple and clean. They are super adaptive. They can constantly learn from new data as the world changes. They also have this incredible fault tolerance. Because all the knowledge is spread out, if a few neurons fail, the whole system doesn't just crash. The network just kind of works around the damage. And maybe the biggest superpower of all is generalization, the ability to take what it learned from data it's seen before and apply it to brand new situations. That's the difference between memorizing and actually understanding.
And you see these superpowers in action literally everywhere. From your phone recognizing your handwriting or understanding your voice commands, to Wall Street firms trying to predict the stock market, to comparing images and, back to that facial recognition on your phone. ANs are already a massive part of our daily lives, whether we know it or not.
But, it's not a perfect story. For all their amazing abilities, there are definitely trade-offs. Training these models can take an enormous amount of time and a staggering amount of computing power. And then you've got the famous black box problem. An ANN can give you a genius-level answer, but it's often almost impossible to know how it got there. And finally, they're hungry for good data. Garbage in, garbage out, as they say.
At the end of the day, it really all comes down to this one idea. The unbelievable power of artificial neural networks doesn't come from one single brilliant algorithm. It comes from their massively distributed structure, thousands of simple parts all working together, and from their profound, almost magical ability to not just memorize, but to actually learn and generalize.
And that really leaves us with a huge question, doesn't it? Now that we've built machines that can learn, machines that can find patterns we can't see, and machines that can adapt, what does that mean for our future? How is this going to change the way we work, the way we create, and the very nature of discovery itself? That's a story that we're all going to be a part of. Thanks for digging into this with me today.